presentation. So how does the venous pressure respond to changes in arterial pressure? It doesn't. Thank you. Actually, I made a mistake when I first read the title of my talk. It wasn't how does the venous pressure respond, it was actually how does the venous system respond? And that is really the crucial issue. I mean, I actually gave this suggestion to Thomas, so I'm surprised I made the mistake. Okay, so the regulated variables in the cardiovascular system, what are they? So oxygen consumption, as we've heard before, must match metabolic needs. Cardiac output varies directly with changes in oxygen consumption. Arterial pressure, as you've heard, is kept relatively constant, which is really quite striking. Your mean arterial pressure hardly changes at peak exercise, which in a young normal male can be 5 times the basal level, and yet you don't have much change in mean pressure. So it's very tightly regulated. Why is arterial pressure so tightly regulated? Well, one is maintenance of brain blood flow. It can be kept constant by adjusting the local resistance, as Michael discussed. It allows an upright posture, but that alone is not good enough because we have the same pressure as mice, and they don't have much of a gravitational gradient. An important part is it keeps a relatively constant load on the heart. And the heart handles volume work much more easily than pressure work. Pressure work costs the heart a lot more energy. So keeping the pressure load constant is very helpful. And also, as Michael said, you can regulate regional flows by changing local resistances. So we function much the way a water system to a community. You have water towers, and what you do in your home is you open up a valve on a sink, a bathtub, a toilet, and that allows that pressure head from those water towers to drain into your system. So that's kept relatively constant, like the water tower, and you adjust the local outflow. Now, just to review the basic baroreceptor reflex, which is involved in this process. So starting off with the equivalent of a rise in blood pressure. So that would be dilating the coronary sinus. And when you do that, you get an afferent activity up through the ninth cranial nerve to the head, and it activates the vagal system to now send down signals, decrease heart rate, and decrease contractility in the upper parts of the heart. So it's like putting on a brake on the system. But where this gets tricky, at the same time, it activates an inhibitory pathway and decreases sympathetic output, which then results in vasodilatation and decreased cardiac contractility, and acts like taking your foot off the gas. So what essentially our system does, it puts the foot on the brake and takes the gas off, and that way it can respond much more quickly. Taking the opposite, what we deal with all the time clinically, is a fall in blood pressure. So what happens with the opposite? Because the reflex really is, oh, I'm going to lose it again. I'd worked it out. I lost the tracing. I thought we'd worked it out, but it's gone. So what you see with a fall in pressure is a rise in blood pressure by constricting the resistance peripherally and then by increasing contractility. Now, this classical description says nothing about the return of blood to the heart. So before I get into that, let me get into this concept here. So here is a bellows which can pump volume out at the top. There's those little carrots there are resistances, so they control the, valves which control the direction of flow. And I fill it with, say, 1 liter of fluid, and I tell you the resistance is a millimeter of mercury times minute times liter to the -1. So what's the maximum flow in that system? And it's really simple. The maximum flow is 0. You can't have flow unless you have a compliant region to allow the pulsatility to occur. So compliance allows the pressure and flow to move through the circulation. It also redistributes volume into different compartments. So now the system is more like this with a single compliance. You can then take up the volume and let it go down again, and that allows the pulsatile flow. Now, capacitance. Capacitance and compliance are not the same. So compliance was a change in volume for a change in pressure. Capacitance in hydraulic systems refers to the total volume, stressed and unstressed, for any change in pressure. Now be careful, in electrical models, capacitance is actually the equivalent of compliance. But in hydraulic systems, which we deal with, blood vessels, it's this term here. It's the total volume for total pressure. So if we're looking at a volume-pressure relationship, in the physiological range, it's a linear relationship, although it's curvilinear at lower levels. So there's an unstressed and a stressed volume on this. Now, if we activate the baroreceptors or sympathetic stimulation, what happens is you tighten up vessels. The slope of the line doesn't change. So it's like you cut out a piece and you make them smaller. So you have the same slope, but for any given total volume, you now have a higher mean circulatory filling pressure. Okay. Now, an important point that we're going to get to now is what's called the time constant of drainage, or tau. So if I have a simple system with flow going in and flow going out, in this system, with an arterial resistance going in, a venous compliance, how stretchy that part is in the middle, and then a resistance draining it. So the time constant is the time to get to 63% of a new steady state. And it is determined by the compliance, the CV there, and the RV, the resistance draining it. So what that looks like on a graph, you would have initial flow on the y-axis, time on the x-axis. I make a step change on the inflow, and the time constant tells me how long it takes to get to, stuck on me. I can't advance.
Could you advance the slide, please?
Froze.
Projector, the positive souvent, s'il vous plaît.
It's frozen. Go back. Ah, there it goes. Okay.
Good.
So that dotted line will be the time it takes to 63% of the new steady state. Oof. What's happened? Yeah. Oh, maybe I just pressed through. Okay. So this is a simple model I've used in the past, which has maybe it doesn't like my finger. So it has a return function, and then it has a, I'm still having.
It doesn't like you.
Mm-hmm. What's that?
Finger.
It's your finger.
I'll try a different finger. So a return function and a cardiac function. But I want to draw this a little bit more realistically, looking at the circulation with the RV, right ventricle, going through pulmonary compliance, going through a pulmonary resistance, and then into a pulmonary venous compliant region, left ventricle, arterial compliance, and back to the systemic veins. So in this system, the total compliance is the sum of all parts. But the part in the venous system creates that mean systemic filling pressure, which is crucial for the return of blood to the heart. Now, that was the basic model you've usually had, but now we were going to take a step forward and make a more complicated one. This was actually brought up by August Krogh in 1912. And what he did, he said, what happens when you have two parallel compliant regions? One is very compliant, you can see that large tub, and the other one is narrower. So the important point in the Krogh model is the distribution of flow between those two compartments is an important determinant of what comes back to the heart, the venous return. Jeez. Okay, so here was the baseline state, and let's say we made right atrial pressure 0, and now we have, sorry, I don't know why it doesn't like my finger.
Stay there, please.
All right. Should I be pressing or just touching? Okay. So now you can see, sorry about this. Sorry, I've now increased the flow to that narrower one, the one with less compliance. And because it's got less compliance, the pressure, the height of the column will rise more. And what that looks like on a venous return curve, it actually changes the slope of the venous return curve. So it becomes more steep when we do that. You want to stand here and maybe just push this? Maybe stand on that side, okay. push.
Poussez le bouton.
Wow. Okay. I don't know what it is, but these are real fingers. Oh, just push.
Are you sure you're alive?
Yeah. Okay. So now we redraw this with two parallel compliant regions. So one was the splanchnic, the SPL, and the other one would be your periphery, your muscle. So we studied this in an animal model, which okay. The person who did this with me was Alain Deschamps, as part of his PhD thesis, who did a superb work on this. So we studied the regulation of the baroreflex in regulating flow with this model. So this is the model. It's a little complicated, and I'm not going to go through all of it, but basically what we did is we isolated the flow from the splanchnic region, which has a slow time constant of drainage, and it's very compliant, and as compared to the periphery, which has a fast time constant of emptying because it's narrower and gets a higher peak. So we went through, oh, maybe that's why. Okay. So I had another hand on the screen. That's the problem. Okay, thank you. That's the catch. So the top shows PCS as the carotid sinus pressure. So we lowered the carotid sinus pressure. We isolated them so we could keep it separated, and we lowered it from 200 to 50 millimeters of mercury. You get the typical rise in arterial pressure you would expect from lowering the carotid sinus pressure. However, the effect of resistance in the splanchnic bed was different than that of the periphery. So because of that, we had more flow going to the splanchnic bed than to the periphery because of that change in distribution. I won't go through this for the sake of time since I've lost time, but we did a series of stop flow measurements, got plateau pressures, we could measure the downstream pressure, we could calculate resistance, we could calculate compliance in all the parts, we could add volumes. And so with all that, what we're able to do is construct volume pressure curves of the splanchnic bed and the peripheral beds. To also do that, we had to put some dye in, and we calculated the absolute volumes in the regions, so we can now have the absolute volume on the volume pressure relationships. And then we gave a series of volume loading, and then with that, you can see we construct these lines, which are the compliance lines of the splanchnic bed and the periphery. Okay, so once we did all that, then the next question was, what happens when we change baroreceptor tone? And what you can hear, it says splanchnic 50, so that was the pressure with a carotid sinus pressure of 50, and then, we started with the 200, and when we lower it, you can see the curve shifts to the left. So that is a decrease in capacitance. You tighten up the circulation, and we recruit unstressed volume into stressed. There's a slight change in slope on this line, which is probably an artifact because at the lower levels they become curvilinear, and that probably modified it. But more often they're actually linear with no change. And then what we did is started off at the low level, we gave an alpha blocker, and we could show that we would shift it back so there was a large component of alpha tone involved. However, that didn't fully explain it, and in some other experiments, we actually added neuropeptide Y, which actually accounted for a further part of this reaction. It's co-released with norepinephrine. So overall, the effect was the increase in arterial resistance with lowering baroreceptor tone. But the striking thing, and a very unexpected one, is we actually saw a decrease in the venous resistance draining the splanchnic bed at the same time as the arterial resistance went up. And the explanation for that would probably be a difference in beta receptors on the venous system going through the liver as compared to the arterial side. So the venous resistance went down while the arterial went up. And then we also had that change of capacitance, which was around 10 mLs per kilo. So putting all this together, what it looks like is this. So they start off with a venous return cardiac function curve. So if you increase the fraction of flow to the splanchnic bed as per Krogh, the cardiac output would actually fall because you've now increased the resistance to drainage, as the Krogh model says. But you decrease capacitance, which shifts the venous return curve to the right, and so that partially compensates. And then you let the splanchnic bed drain better, so you make it a faster time constant, so that restores the slope back again, and so you get this rise in output. And then if you add in an improvement in cardiac function with an increase in heart rate and contractility, which we kept constant in the experiment, but if that was there, then you get an even bigger increase. Now, so what are the implications of this? Well, first of all, giving the baroreceptor activation is very similar to giving catecholamines. This was a paper we did in 1999 where we studied norepinephrine with sepsis or endotoxin with and without nitric oxide synthase inhibitors, but I just want to show it in the point being that cardiac output rises. That's the C on the top. It also rose when with endotoxin, although the nitric oxide synthase inhibitor, L-name, completely blunted it. And we were able to do venous return curves with these and put them together. So what are the limitations that we would face at the bedside? So first of all, capacitance, a decrease in capacitance will increase venous return, as I showed you. But you have to have the reserves. If you don't have that volume, that reflex can't act that way because there's no volume to recruit. We said there was, if you decrease splanchnic resistance, you will increase venous return. But the problem there is, if you're giving a lot of catecholamines and you've already made that tight, it's going to counteract any of that reflex mechanism to actually change that. So you could lose that benefit. So that will not be effective if the subject is getting strong alpha agonists. And then the other part is, you won't get a change in cardiac output if cardiac filling is limited. So if we just looked at this and the cardiac filling was limited, then you could have all those venous changes and nothing will happen. So the heart has to be able to respond to take more. So the clinical implications, just to summarize then, the action of vasoactive drugs are dependent upon the baseline sympathetic tone, the volume reserves, and cardiac function. Capacitance changes can only occur if there's sufficient unstressed volume to recruit, and I think that has to be part of your plan when giving actually volume and you're managing your patients. Improving cardiac function, heart rate, contractility, lowers the right atrial pressure and allows more volume to come back, but it has to be able to respond. And raising arterial pressure, as you've heard, increases the LV afterload and can actually decrease the output benefit. And if cardiac filling is limited, improving return function will not increase cardiac output. And infusions of catecholamines are not identical to sympathetic activation. For example, I pointed out that neuropeptide Y was released also as well with the neurostimulation, and it's a potent constrictor. And the distribution of flow change with norepinephrine infusions, you're going to affect venous return, as I showed you. And what happens at high doses? Do you lose that selectivity where it was affecting the splanchnic bed different than the peripheral bed? Beta agonists increase the venous drainage from the splanchnic bed. Alpha agonists decrease it. And raising arterial pressure increases LV afterload, as I already said, actually, and decreases LV output. Thank you.